Thanks for coming. So today I'll be presenting a topic about weaponizing Apple AI for offensive operations, right? So I'm a lead red teamer, work for CVS Health, and I'm specialized more in post-exploitations and techniques that usually defenders don't see, right? I used to write blogs, and if you like my work, and also, by the way, all my code POCs that I'm going to present today will be posted in my blog, and if you like to take a look at it, you can follow my blog. Or if you're into red team space or AI researching and stuff, you can also follow me on LinkedIn, right? So today, I'll be discussing more about Apple AI stack as an overview, like what are all the frameworks are there and native components of Apple. And the main component is CoreML, which is a legacy framework. And we'll see how we can weaponize that for C2 operations and payload staging. And also, there are other native frameworks called Vision and Foundation, which is now built for Mac. And we'll also see how we can weaponize that for other offensive purposes, right? I also built a framework called MLArc. It's a C2 framework, which completely works based on CoreML. And I'll show you a demo how this works and how payload staging can be performed with MLArc and communicates completely with native Apple APIs. Right. And also, in case if you don't want it to use MLArc as a C2, we can also use Mythic Apfell Payload and see how we can embed that payload into the ML model and see how we can weaponize that for offensive purposes. So all this will be demoed as well, and the code will be posted in my blog. And also, as an end, we will also discuss about detection blind spots and how we can mitigate this from a defensive side of it. Right. So AI stack overview. So there are multiple components when it comes to Apple AI. The legacy component is CoreML engine itself. It's a lightweight, shipped with iPhones, Mac, and used for day-to-day normal activities, been used by iPhone photos and other applications. And also it's been used by third-party applications as well. And there is a newer framework called Apfell Foundation model, which is like a large-scale model, which is used for other large-scale activities, but it is like closed, private, and it is used only by Apple. So we'll be targeting more on the CoreML engine rather than the latest one, because this CoreML engine is still available on all the latest Mac, and it can be weaponized. On top of it, there are other frameworks that you see, Vision, AVF, and Reality Kit, Photos, Siri, and all those things were there. Those are all native frameworks of Apple, and I'll be picking up only two, in this case, the Vision framework and also the AVF, and see how we can weaponize that. So what is an ML model? So ML model is CoreML model, so it's used by CoreML model engine. So if you look into Apple MacBooks, there are tons of ML model files sitting on your desk, which been used by different applications for different purposes. It is a lightweight model that will be shipped along with your applications. And it's designed for fast and on-device executions, and it is very lightweight, so it can be even run on mobile phones. So whatever that we're going to discuss, it is still applicable on the mobile devices as well when it comes to offensive purposes. The assumptions are, the model file is not signed, so the gatekeeper or the notarization does not check whether the model file, whatever your application is loading, is signed or it is secure. So that's what we'll be using that for offensive purposes. So there is another format called MLArc C, which is a compiled format of a ML model file itself. And that is also, if you look into all your MacBook applications, most of the files you might see .ml model or .ml model C, which is it's a compiled version of model file. That's it. All these are non-human readable. So even if you try to read the model file, you need a CoreML framework to load and read the content of it. So what's inside on a model file? So there are multiple components involved, and the core components are the model descriptions, which have your names, types, what this model is all about and stuff, and the model type, and the model parameter. So the model parameter is the core parameter, which actually sets all your trained data will be sitting in your model weights. And there are like 10 to hundreds of model layers that you can use in that particular parameter. But this is where all your payloads can sit as a model weights, and I'll be showcasing how I'm going to weaponize that as a model weight and see how we can put a payload, encrypted payload, and see how we can bypass all those things. And there are metadatas, and I'll be demoing two things here. One is how payload can be injected in model weights, and another one is how payload can be injected in metadata of a model, and see how we can load the model and execute the payload, right? So how an ML model works. So basically, when you're building an application, you wanted to use Apple AI for efficiency. What usually the developers will do is they will use a model file, ML model file that they can create, and train the model and ship it along with your application. Compile it into a model C file or in a model file, and then you can ship it with your applications. That's what when you try to load, along with the application, the model file will get loaded and executed in memory. So the next one is the Vision framework. It's not an Apple AI stuff, but it can be used for sending data to CoreML pipeline. So Vision framework is used for vision related activities like photo processing, image processing, and stuff, and text recognition. And it is a lightweight and very silent. It has its own native APIs for processing all the data. I'll be showcasing how we can embed a data into pixel on an image and how we can extract those pixel data from using that Vision APIs. The next one is the AVFoundation. AVFoundation is used for audio-video processing. There are many applications uses AVFoundations as of today, like Zoom, CapCut, and iMovie. There are much more applications uses AVFoundation. It is again another native component sits in Mac and used for audio-video processing. So I will be demoing on how we can create an audio file, and instead of putting an audio payload into a metadata or a description or somewhere else, we'll be putting a payload directly in audio synthesis, and then see how we can extract that using the AVFoundation libraries. So abusing each layers. The first one is the model file. Like I said, we can place payloads either in the description or metadata or in the model weights. Each layers have different types of formats. So for example, if you are placing your model, if your payload into your model weights, it will be a float variable. So if someone try to read it, all they see is a float data, that's it, right? And the descriptions has its own way of formatting. Likewise, we can place your payloads on every layers of a model file. And why no one able to read this? Because EDR or AV engines was unable to detect these kind of things is because it actually need CoreML libraries to read the model file and extract the data. And the Vision framework. So like I said, Vision have its own set of APIs, which is used for reading, extracting data from an image. And we'll be using Vision's libraries to extract an image, read an image, extract the pixel data, and put it in a readable format. So each component used for different purposes, and we'll be showcasing everything on how we can now exploit it. So for example, when I say pixel, you create an image, and you set the opacity like 15%. So when you open that image looks like a readable image, like it's not a corrupted data or something. You can still view the image, but the payload actually sits in the image as a pixel. And for simplicity purposes, for demoing, I set it to 15% so that you can see literally what's happening, what is sitting there. But you can also set it to like 1%, so it's not visible to human eye. So if someone tried to open that image, by default it look like a legitimate image, or you can inject the payload into a logo file of your application and ship it along with your application. So during your runtime process, you can extract the payload from the image using this native API, and which looks completely legit. And the AVFoundation is kind of something interesting. It's not a steganography. I mean, it's kind of steganography, but it's kind of a bit more advanced, because what I'm doing is we will be placing a payload as an amplitude. For example, I have a payload like hello world or something. What I'll be doing is take the payload, convert into a binary, zeros and ones, and the one represented as like 1.0 as an amplitude, and zeros represent like 0.2. So which is kind of loud, 1.0 is kind of a loud, and 0 is like a quiet mode. So when you play that audio, it still plays in VLC or something, whatever you play it still plays. All you hear is a beep sound, like ups and downs of beep sounds. But you can use AVFoundation as a framework, read that audio file, extract the payload, and decode that, and then pass it for further operations. So you can, it's more like a steganography, but it's kind of a bit of advanced because the audio files still look legit. It's not a metadata or something. We are actually placing the payload into as an amplitude of an audio file. All right, I'll show a quick demo of Vision and AVFoundation, how this thing actually works. All right, so I have a Python script that actually uses Python libraries to generate an image file. So when you run this code, it will just create an image. And if you look into that image, it's like a normal working image, and it's not corrupted or anything. All you see is pixel data which have a payload in it. So in this case, I'm hard coding encryption key for my payload, which I'll showcase how I'll be using this. But this is just not an example, like how you can place a payload or a key or something on an image as a pixel, and how we can extract it. So to extract it, you just I wrote another script in Python, which uses Vision libraries to read that image and extract that payload from that image from the pixel, right? So this is how you can use Vision to read and extract payloads during execution of your payloads. So the next one is the AVFoundation. So this I created a two Swift code. One is to generate an audio file, and another one is to read the audio file, extract the data. For example, what the script will do is, I have a payload called hello world, and what I'm doing is I'm converting that hello world into a binary, zeros and ones. So if you look into the code, so zeros are representing as amplitude of 0.2, and the one bit is representing as 1.0. So when you play this audio file, all you see is like a beep sound, but technically, no, it's not corrupted or anything. Even during the deep analysis, you're still unable to extract what exactly sits inside that audio file. But through audio in AVFoundation libraries, you can pass this file. So I have written another code to read this audio file and extract the payload. So what this will do is, it will read the audio file and extract all the binaries, and decode that binary and extract that nucleotext data from that audio file. So the audio file look legit, and it's not detected by any of the scanners, but you can still send literally like 1 MB of payloads in an audio file and extract it through AV Engine. All right. So the next one is an MLArc. So MLArc is, I wanted to test all this hypothesis, like how this ML model itself can be weaponized for payload executions and C2 operations. So this is lightweight C2, which is written in Python, and it's uses a fast API for communication between the client and C2. So instead of JSON or DLL, we'll be using model file as a payload transmission mechanism. So what it will do is, so consider we have a C2 and an agent. So we have a dropper, like dropper is written in Python. So when a C2 is running, and you run the dropper on one of the victim system on a MacBook. So as soon as you run it, it will go and register to my MLArc C2, and it will register a session. It will create a session for you. And then if you want to send a command, for example, I got a session and I wanted to send a command like who am I, or something from my C2. What my C2 will do is it will take your command, convert it into hex encoded or ZAR encoded, and then place it into model metadata. It will create a model file in memory, and then place the payload into model metadata, convert that model file into a binary, and send the binary over the network, right? So on the victim side, the victim receives that binary, recreate that model file from the binary, and use CoreML libraries to extract that hex encoded data and decode it, and then execute it. And then what it will do is, it will again send it back the output to the C2, again through ML model. So again use CoreML libraries to recreate a model file by placing the output into the same way, vice versa, and then send it back to the MLArc. So MLArc again use CoreML engine to decode it, extract the output, and display it to you. So that's how this MLArc C2 works. So I can show a quick demo of how exactly this is working. Right, so I have a server which is written in Python, and also the agent is written in Python. So when you execute it, the server, all it does is, it just listens for client communication. And then on the other side, I go to an agent. Again, it is written in Python. As soon as you run it, it will create a session for you. And go back to your C2 server, and you'll see, there is a callback beacon from one of the agent. And then, to connect to that agent, all you do is just connect and pass the session ID, and now you are connected. Now, if you want to send a command, like for example, I'll be using ls-la as an input. And what's happening is, as soon as you send a command to the C2, C2 take this command, create a model, inject the data into model metadata, and then send it to the server. Convert it into binary, and the binary value will be sent it to the server. And sorry, send it to the agent. So the agent receives it, decode it, and run the command for you, and then take this output, and again, put it in a model file using CoreML libraries, and send the raw data, binary data to the server. The server, again, like I said, it will extract that using, again, CoreML engine and display it to you. So this is completely, this MLArc C2 is completely work based on CoreML libraries, and it is completely stealthy. It's been tested against latest EDRs and AV engines. None of them been caught. All right. Okay, so in case if you don't want to use MLArc as a C2, because there are hundreds of C2s available as of today, and you don't want to use MLArc, which makes sense. So the well-known C2 for Mac is Mythic, and Apfell is one of the well-known payloads. So if you run Apfell as a standalone, like raw Apfell code, it will get detected by latest EDRs. So to bypass that, what you can do is you can take the Apfell code. So what I'm going to do now is I'll take the Apfell code and encrypt it using XOR. I will place the XOR key into an image file, and then use Vision Framework to decode that payload. So first, generate a key using image, and then place the key in an image file. Next, take an Apfell code, encrypt it using XOR, and then put it in a text file. Now you have your encrypted code as a text file and your key. So now what I'll be doing is take that encrypted file, use CoreML libraries, and generate a model file, place the encrypted code into model weights, and then send it to the loader, right? So I can show you a quick demo how this thing works. So first thing, you generate a key. This is now already we have seen, like how we can generate an image using Python. So this image is placed, called XOR key, the same thing that we've seen already. This is the key that we're going to use for encoding the Apfell code. Next, we will be creating encrypted text file. Like take your Apfell code, means apfell.js, and take the JS file, use XOR encryption, use the key, and encrypt that Apfell code. So you will see a text file got created, which contains your encrypted Apfell code. Now, you need to embed that Apfell code into an ML model. So what the third step will do is, there is a Python script which uses CoreML libraries. It will take the encrypted code from the text file and place it into model weights and generate a model file for you. So this is the .ml model file, which you can ship as part of your loader. So now what your loader will do is, it will take the ML model file and your image file. Like consider you're building an application and you have your model file along with your application, and you're sending it to the victim. So the victim, you can place your loader, like a post runner or pre-runner along with your application package, bundle it, and send it to the victim. So when you run it, all you need is the model file and the image file. The image file, you can place it like a logo or something, right? Now, you can completely execute this in memory. So what I'm doing is I have another loader. What this is doing is, it takes the model file, takes the image file, use Vision to read that key, and then take the model file from, use CoreML to load the model file in memory, and decode it completely in memory, extract the payload, and pass it for execution. right? So as soon as you execute it, you'll get a beacon on your Mythic C2. So this is how you can run Apfell by embedding into a ML model file. And this is completely stealth, and it's never been detected during any of our operations. All right, detection blind spots. So these model files are static files which never been scanned by AV engines or EDRs, because even if you scan it, it is really hard to find what is sitting inside. And this audio files, again, it's a legitimate file. When you play it, it still plays, so it doesn't look fishy. And also the same goes for the image file as well. So you inject your key into an image logo or something, and you send it along with your package. The logo looks legit, and the image file never been detected as suspicious, right? So MLArc uses all these techniques, and that's how we were able to bypass all the EDRs as of today. So as a mitigation, I would say look for what is actually loading the ML model file and where this model file is from, and look for APIs that these applications or the loader is using. Like look for suspicious API calls. Like if application doesn't need to load image vision libraries and why it is calling, look for those suspicious API calls which has been used by an application, and that's how you can detect. Because this is not just another attack or technique. This is if you look deeper, this is like a supply chain attack. It can also be a supply chain attack. So there are hundreds of model files being posted in public forums, and the developers is blindly loading those model files for their day-to-day work, and this also can be a supply chain attack, right? So, so to detect this, always look what APIs are being called and whether it looks suspicious or not. Apart from looking for just is it a binary or DLL, look what is doing and whether this image file or model files look legit or is actually needed for that application. And that's how you can detect it. As of today, none of the EDRs or AV engines scan for model files, and that's why you can weaponize this, and you guys have to write custom rules to identify these kind of attacks. That is all for the talk today, and I'm happy to answer if you guys have any questions.